This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio.
Welcome everyone to the Software Engineering Radio show today. My name's Kim Carter. I'll be your host for the day. And we've got Michael Hausenblas as guest today. Michael works at Red Hat in the OpenShift team. He's a Gopher, that's a Golang programmer, a cloud native ambassador, and Michael tries to help folks to be successful with container technologies, including Docker, CRI-O, Kubernetes, and OpenShift. Michael has written books on container networking, Kubernetes, and serverless ops. Welcome to the show, Michael.
Thanks a lot for having me, Kim.
We've had shows on Docker with James Turnbull. That was show number 217. And we've had Docker Security with Diego Monica. That was show number 290. And another show we've had that was related is Network Security with Haroon Mir. That was show number 302. There's a relevant article from the IEEE Computer Society on today's topic. That's Docker. And another one, network quality of service and Docker containers. Today we're going to be discussing container networking. So I'm just starting off with the container networking stack. What is container networking and why do we need to network containers?
Right. Let's step a bit back. So what are containers? Essentially a way to handle application level dependency management. So, if you, for example, know Python and, you have virtual envs there where you can create virtual environments for Python rather than polluting the global space. That's the same thing with containers, just for any kind of language and binaries and so on. So containers package your application level dependencies nicely. You can ship them, works the same on your laptop and on production everywhere. And at the end of the day, you can run a container on your laptop and, you can run a bunch of them, or you can run many of them, and then you need container orchestration, the things like Kubernetes that actually manage these containers for you at scale. And one of the big challenges there is actually how these applications in the containers communicate with each other. And for that, we need container networking.
Cool. So let's talk a little bit about the networking stack and what it's comprised of when it comes to containers. Can you explain briefly the three layers? So that's a low-level networking, container networking, and container orchestration.
Right. So in all honesty, this is not not something like the OSI stack or TCP/IP stack, something official. This is just something I came up with to easier explain stuff and make it easier for people to understand what is going on there. So the way I approach it is to look at lower or low-level stuff. That includes everything, right? You have the networking gear, the actual hardware. You might have virtual machine, virtualized stuff in there. You have IPTables, you have Linux kernel features in there. You have routing, you have Linux namespaces, C groups, and so on. So everything, all these bits and pieces that usually from a developer perspective, you don't really care about. You don't actually see them, touch them usually. But they exist, and you should be aware of them. There is the container layer that is mainly around the actual container runtime. So the thing that essentially made Docker, popular and big. Nowadays we have OCI, the Open Container Initiative, and we have Rocket, and we have a couple of specs there, and I believe we get to that back later on, the CNI and CNM.
Yeah.
So this is everything around the container runtime, really, on that layer. And on top of that, as I mentioned already early on, if you're not manually launching a container here or there, but you're kind of like on an industrial scale launching and killing off containers, then you have a container orchestration system like Kubernetes in place, and there you have the actual container orchestration layer. So everything around service discovery, ingress, egress, how you compose things there. It might go so far that you have service meshes there that even sit on top of this container orchestration layer, or some people consider them part of it. But it helps to think along these three layers because they typically are owned by different either stakeholders or different people focus on them.
We talked a bit about how most networks today are becoming the responsibility of software engineers. That was in show 302, Network Security with Haroon Meer. I also cover this in my book on cloud security. Can you explain what software-defined networking is and why software engineers need to understand about it?
I'm not sure if many people will be super happy with my definition of it, but at least that's how I see it. To me, it's mainly a marketing term, to be honest. It's a useful term, but it's almost like the term overlay network. It's pretty broad, and depending on who you talk to, which vendor you're talking to, and so on, you will hear different things. Different people. If you ask someone from Cisco and whatnot, you will hear different things. What I will say is the most important characteristic, and that's what we are leveraging in the container world, is that rather than being confined by the physical things that are in there, like a physical NIC and actual cables and so on and so forth, you are on a virtual level, right? You are essentially, you can via software define pretty much everything. You can say, hey, I want to have three NICs here. You define endpoints. You can give IPs to containers and so on and so forth. So routing tables, everything is on the software level. Everything is super flexible there, and that allows and in the container world with a container orchestrator with many containers that come and go, this is really the only way to go about. You cannot manually keep up with the pace that is going on there. So in a sense, as I said, it's as with many other things like overlay networking, it's a bit of a marketing term, but the main thing really is you're much more flexible and can automate the heck out of it.
So you'd use tools like Terraform and that sort of thing to build up your networks as software, right? So that you can basically repeatedly create them. Is that pretty much will sum it up?
Yeah, and it goes even further, because if you think about like 5 or 10 years ago, or maybe 15 years ago, we might have had like a handful of virtual machines that we would manage. That would stay around for months or years. And now with containers, we have hundreds of containers, if not thousands of containers that might only stick around for a few minutes, right? So you do need this flexibility. You do need this velocity there. Mm-hmm.
So we're just going to move into a section on single host container networking. So there's 4 single host networking modes based on the 4 Linux kernel network namespace drivers. They are bridge, host, which is faster but less secure, container, and none. Can you give us a description of these modes and what they give us, how they work, and where we would use each one?
The background here really is that these 4 modes that you mentioned are essentially have been popularized or have been established by Docker, what Docker shipped with its runtime. So bridge, which is still the default, essentially sets up a pair in the container, which is essentially a network namespace, and the host. So you have that pair there, with the obvious advantage that you're pretty flexible in terms of ports. So you don't need to, you can have, for example, 2 containers that both serve on port 80, right? So that's something that you usually cannot have. Besides the fact that you usually cannot bind below, unless you have privileges below port 1024. Host networking, if you essentially say it's fine, share the network with the host. You don't really care too much there. It's definitely faster than bridge, but you don't care too much there in terms of security, because you're essentially effectively removing the isolation there. Container, that mode is essentially reusing an existing network. So you cannot, in a Docker file, whatever, you cannot create that. only at runtime you can say, here I have another container already running. Please join this other network here, and we're using that in Kubernetes very heavily. So there is actually a component in every pod there that spans up this namespace, and every other container in that pod joins that one. And non-essential means disable. It's still there. The network stack is still there. So you do have loopback interface if you do, if config whatever IP command, but that's all. You cannot use any network. You don't have any external communication there.
Yeah.
So that all of them are really useful one way or the other. If you let's put it in a very simple terms. If you're doing stuff on your laptop, right, then you're fine, right? In any kind of clustered setup, if you have a bunch of machines somewhere, even if it's just a 3-node cluster, none of them, right, is really, really useful, right? You would use others. There are a couple of them in Docker, like Overlay and MacVLAN, IPVLAN, and there are third-party plugins possible, a couple of them there. But essentially, for this use case of running a handful of containers on a single node or on your laptop, one of those 4 might be useful.
So the container networking modes basically means every container shares the same network stack, right? So they all have the same IP address.
Mm-hmm.
So how do you actually differentiate the containers? Like, how do you actually contact them? It's just by the same IP address but a different port, is that it?
So they, like the containers themselves, they get with the bridge networking, they do actually get their own IP address. It's really just that essentially, you essentially have this VF pair that is, one part is effectively you have 2 namespaces, right? The one being in the container, the network namespace in the container, and the other one being in the host. And through the VF pair, these 2 can communicate. And the IP there is really host local, so that doesn't go beyond that host. So you need to have some, if you actually want to get traffic to that into that container, you need to do something outside of that. But I like these 4 local local container Docker network modes are nowadays, unless, as I said, you manually launch a container on your laptop, not that interesting or widely used, right? You're really looking at Overlay or whatever in a clustered setup when you're actually running containers in production, right?
Right. In terms of allocating IP addresses, the bridge mode mostly takes care of this. What about the other modes?
Right. So there, again, it very much depends on what your setup is. If you have a single host, so again, think of your laptop, you typically, you find you can manually do that. You carve up a certain range, in the private IP address range, and you're fine. In a distributed setup, that is something completely different, and there it's mainly about either your network plugin or third-party solution like Calico and Weave and Flannel and whatnot. They provide something like that out of the box, or the respective container network standard like CNI or CNM have respective support for the plugins that do that. So IPAM providers that actually manage IP addresses throughout the cluster. So they might have a separate database, for example, and assign entire IP address ranges to nodes, or there is some gossiping going on, or whatever the actual way of spreading and managing these IP address ranges at the end of the day is. But the big challenge really is in a distributed setup where, especially if you're hitting hundreds and more nodes, you don't want to manually arrange that. And in Kubernetes land, it's even more complex because you're essentially dealing with 3 different and distinct sets of IP address ranges for the hosts, for the pods, and for the services. So depending on the container orchestrator, you might need a more complete or advanced solution to manage these IP addresses ranges.
Yeah, okay. In terms of managing ports, we have fixed and dynamic port allocation. Mm-hmm. How do each of these work, and in which cases would we use each one?
Right. So, as I said, with bridge mode, you're fine because since each container has its own just local but private, but has its own IP address, you don't need to worry about that. With host mode, you obviously, since you're essentially reusing or sharing the network with the host, you need to take care of that. You need to manually allocate the ports. You need to say, okay, I can only have one web server on port 80, for example, or whatever it is. The container one is special because there it really depends on what you're reusing. If you're, for example, in Kubernetes land, it's not a problem because there the policy is IP per container, or technically per pod, because all the containers in a pod share one IP address. And with none you don't have that problem. But the biggest difference here is really host versus bridge. So that's why I guess why bridge is still the default if you have a single Docker daemon there, because people don't need to worry about allocating the ports or managing the ports. They can just each of the containers can simply use whatever port they like. I guess that's one of the motivations why it's still the default there.
There's quite a few things to consider in terms of network security with Docker containers. By default, containers on the same host can communicate with each other due to the --i switch equals true, which means comms work by default. But there are risks that need to be considered. Can you talk a little bit about these risks and how engineers can mitigate them?
Right. I have to say that many of these things some of these things are really more of historical interest rather than going forward. Things like links, for example, between containers have been deprecated, so that is not an issue anymore. It's still there, so this inter-container communication ICC is still there. This flag is still there. So if you do set it to true, what it effectively means at the end of the day is that the Docker daemon there will add a default rule to the forward chain in IPTables that effectively accepts everything there. And if you set it to false, then it will have a drop in there. So if you don't want that, right? If you don't want that in the forward chain, then you want to have ICC false, and with that all the implications. So unless you have a really good reason to have it, just you know what you're doing and you have a really good reason why you want to have that, essentially being able to coming from one network interface going to another network interface, by default all the packages are accepted, you probably want to set it to false anyways. Right. And as I said, some of the issues that were there initially around the a very primitive way of service discovery, which is called links, which essentially only worked on a single machine. So you could.
How do you spell that?
LINK, like a link, like on the web, a link. So you can link containers or link Docker containers. So essentially the idea was that you could explicitly say link this container to that container, and then these two containers can directly see each other and talk to each other via this name. And since it only works on a single host or single node, and the B it's really manual and brittle. This link-based service discovery and linking of containers has been deprecated anyways, and with that, quite a big chunk of the issues around inter-container communication have gone away anyways. Yep. But it's still there, so probably best set it to false, or I would at least do it.
Okay, so if one container gets compromised, it could potentially access other containers on the host and compromise them as well. What else do we need to be thinking about in order to provide solid configuration and mitigation around this?
Right. So again, difference between one single node and multiple nodes, where multiple nodes you typically have to take into consideration what kind of container orchestrator you're dealing with there in terms of what service discovery is offered and so on. But in the simplest case for a single node, think of the many command line options. And as I said, I'm not very familiar with the most recent version, but what the defaults there are. At the end of the day, everything what's happening there is just essentially a fancy way to manipulate IP tables. So if you are a network security guy who your IP tables, then at the end of the day, you can just look at what, with certain settings, defaults or whatever, what is the result in IPTables. You see all the rules there, and with that you have a pretty good idea what is going on, what is allowed, what which containers can talk to what, can you do something from the host, and so on. In general, because you you are dealing with a daemon there that runs on the host, you have an attack vector there, so anyone who has root access there can essentially own all the containers there. So you really want to make sure that you don't have that available from the outside world. There are other setups that are possible that do not use this daemon-based approach. There's Rocket there in the context of Cryo, which is Kubernetes specific. We have non-daemon based systems. From a security perspective, this is certainly something that is worrying. Up to a certain Docker version, it was also the problem with upgrading this. So you might have figured there's a bug there, or some security patches necessary, but you couldn't really upgrade the Docker container runtime while the containers were running. You had to shut down all the containers. So people would probably wait a bit longer than is advisable to upgrade. So there are a couple of implications with these big fat daemons, as my colleague Dan Walsh likes to call them. And yeah, so in a nutshell, that is for a single node, that is the case. It gets more interesting and more complicated in the case of multiple hosts and container orchestration system like Kubernetes.
Yeah, so we're going to dive into the section basically in your book around multi-host container networking. Just before we do, can you give your listeners a quick explanation of what IPTables is?
In the simplest sense, one could say it is an Linux kernel level way of how to route and pre-process network packages that come in from a network interface and may, on the one hand, be forwarded to a local process. So that would be pre-routing in the input, or from one network interface, another network interface that would be pre-routing, forward, and post-routing, or from one local process to another process. So that would be output and input. So you have different ways how you can route these package. And essentially what you're doing there is you have that's the tables element. You have a long table where you have rules, and you say, if something comes in from that network interface and has this destination and so on and so forth, then drop it or forward it or whatever. And this, although it's from the UX not very cool or interesting or whatever, this forms still pretty much the basis of pretty much everything we have there. There are nowadays IPVS based Docker Swarm has that, and in Kubernetes we have that. We're starting to see support for that as well, simply because IPTables has a certain, depending on how you use it, you see a certain limitation. For example, in Kubernetes land, you have that. You have entries, a couple of entries for each of the services on every node. And if you're hitting like 10, 20,000 services, you have a very long IPTables there, and it just takes quite a while until you find something there. So if you have many services and you have many entries there, you really want something else like IPVS. But nowadays I would say it's still more or less the standard way.
So you've mentioned IPS. Can you explain that a little bit?
IPVS is essentially a more effective way to go about it. At the end of the day, has the same underlying kernel structures that are manipulated, but it's rather than having a linear search through these tables to these rules there. You have I can't really talk about the details how it is implemented. It's a more effective way to go about that. This problem of defining how the kernel is supposed to route the packages, on the one hand network interface, and on the other hand local processes. And I'm not an expert there. The only thing I know is for sure that apparently for large scale services, if you have many of those, then you need something like that. I'm not saying that this is the only solution. I'm just saying I've seen it. It is already part of Docker Swarm, and in Kubernetes land, this was actually work led by Huawei. They pushed that quite a lot. That IPVS is, establishing itself as an alternative to IPTables based routing there.
Can you explain what an overlay network is?
Right. So where do we start?
I know you mentioned it was something around a marketing talk and that, but there must be a little bit more to it than that, yeah?
Yes. So in the widest sense, like if someone hears overlay, then the question is, what else is there? Is there an underlay? And indeed it is. So obviously, before we had overlay networks, and there always will be the underlay, so the actual stuff, right? The wires and NICs and all the stuff where it's actually happening. In the widest sense, if you think about it, also the internet is an overlay network, right? VPN, many things count as overlay networks. In the context of container and container orchestration, we typically think of a stricter set of overlay networks. And, there are many ways how you can differentiate them. You can look at what level they're operating and so on and so forth. You can differentiate between VXLAN or UDP overlay and so on and so forth. So there are many different ways. Docker Swarm has its own Docker overlay network built in. It has its own key value store. And one thing that one should not forget with an overlay network, you need some kind of typically key value store, distributed key value store, which in Docker's case is essentially built-in Raft-based. Usually in Kubernetes land, we're more or less leveraging etcd, which is also Raft-based key value store, but which is separate process outside. And yeah, so you need that to keep essentially the state. You need to know, you need to remember who has what, and all the assignments and so on. So you need some kind of distributed, typically key value store, as I said. So this overlay network essentially defines a virtual network, if you want, a software-defined network on top of the underlay, on top of what is actually there, on top of what is the actual wiring there. And this means that it's super flexible. You can define, depending on the properties of your overlay network, pretty much everything as you need it. You can throw it away. You can immediately program it in a way that it accommodates the velocity that you see in container land. So in a nutshell, overlay network, a virtual, very highly configurable network, software-defined network on top of an existing physical network. If that makes sense.
Okay, yep. What does Docker support for overlay networks look like?
Right, so you have a lot of players in that space, and it hasn't really, I think it has even gone up in the last couple of years. You have on the one hand the established players, right? Of course you have, the Cisco's and others there. But interesting, there are a range of startups that have done incredible innovations there. Chorus, for example, with Flannel. WeaveWork with WeaveNet. There is MetaSwitch project Calico there. There's OpenVSwitch, which is now part of the OpenStack project. There's OpenVPN. There's Kennel, which is essentially a kind of joint work between Calico and Flannel. There's Romana, there's Cilium, which is eBPF, or BPF based, as I have learned. You don't say the E anymore. There's Aporeto. There are tons of these services. So essentially, if you're talking about Docker proper, you essentially either use the built-in Docker overlay network or one of the third party, as I said, Calico, Flannel, WeaveNet, and as I said, Cilium being a rather recent addition to the whole circus, but a very interesting one because it's based on eBPF.
Yeah, so you talk about these quite a bit in your book as well, don't you?
Yeah, a little bit, but to be honest, since it's such a fast-moving space, and projects are merging and this and that, and adding support for everything, a book can never actually keep up to date. Even a website is, you would need to update it pretty much every day or every other day just to keep up to date. So I think the best that you can do in that space is, if you have already experience with something or preference for something, go with that. Or you use the stuff that comes out of the box. Docker typically has that, right? Has batteries included, and then you have third-party integrations or plugins that you can use. I think with many things, it's a bit of a taste thing, right, or preferences thing. So some people find the one solution or the one approach cooler. Of course, there are differences, right? So there are Calico is always focusing on or is always focusing still on policy stuff, whereas others, like Flannel's trying to be very like Unixy in the sense of that doing one thing, easy, simple, small, not trying to do everything. And depends. Some people prefer the one or the other. All I'm saying is that there are many things to choose from. You might end up using or evaluating 2 or 3 or 4. I wouldn't be surprised if you do. And then, stick with what you have the best experience with.
Yeah. Right.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio.
Could you give us an example of one of them and how you go about basically creating an overlay network with one of those projects? So like what are the steps involved?
Right. Big ones, right?
Yeah.
So you have Docker with the CNM, the Container Network Model, which essentially, is this one company that has established this standard and follows there, right? And the canonical implementation there is the lib network. And there are a couple of plugins. Weave has Contiv, Calico, PlumGrid, and so on. And then on the other hand, which originally came out of Kubernetes, but nowadays is a wider accepted standard, supported by many different orchestrators, including Mesos and Cloud Foundry and so on. Is the Container Network Interface (CNI), and again you will see many of the same players that you see in CNM land, like Weave and then Calico, and then many more plugins from others. Because CNI is very, very lightweight. It's essentially just a very, very simple interface to add or remove capability there. And so depending on which one there you're using, so if you're using, for example, Docker Swarm, which obviously supports CNM, Docker's network model, that looks totally different to if you're using CNI with Kubernetes. Even if you're talking about the same thing, right? If you're looking at Weave, how to deploy that as an overlay network on Docker Swarm or as a third-party plugin on Docker Swarm versus CNI on Kubernetes, that looks different. And so it's not so useful to say, hey, this is, of course you can say here are the commands. Here, it's Docker create network or network create. I can't remember the syntax there anymore. And then, depending on if you're using the built-in or you're using a third party versus CNI, which is very lightweight. You essentially have just a JSON file where you have the configuration, and then you say, hey, do that for me. And the interface really is essentially just passing over that JSON file to the container runtime. And the container runtime then goes off, does things, or better say in the other direction, the container runtime says, hey, here I want to have this and this done. And the respective plugin then does something like, IP allocation or overlay network setup or whatever, and then reports that back to the container runtime. So depending on the model, in a nutshell, trying to answer your question, depending on the model used, CNM or CNI, the actual steps look pretty different. The only advantage that you have probably is that if you are already using a concrete project or product, like let's say Calico, then moving from one, orchestrator to the other might be simpler because it's just a difference in terms of how you set it up, how you enable it, but still the underlying characteristics in terms of, latency, scalability, reliability, and so on and so forth will be the same. So it's certainly a good thing that both network models, container network models, essentially, in a nutshell, work pretty similar.
Right. So what's the difference between an overlay network and a swarm?
So Docker Swarm, nowadays, this is really the entire container orchestrator, right? And one part of that, of Docker Swarm and Kubernetes and Mesos and Nomad and many more, is how to either out of the box or through third-party integrations enable the multi-host container networking, right? So you could have, like in Docker Swarm case, you could have the overlay network built in, where it has the key value store and everything more or less directly integrated, whereas in Kubernetes land, you have these as separate components, right? You have the API server, which is one binary. You have etcd, which is one or more other binaries running somewhere else, but still having the same functionality. So it's kind of like monolith versus microservice architecture. But Docker Swarm really being the entire container orchestrator where networking, enabling this networking, being able that the different containers or applications running in different containers on different nodes can communicate with each other, and also ingress obviously is part of the responsibility of a container orchestrator.
Okay, cool. How do we go about encrypting traffic between all containers on an overlay network? I'm assuming this is going to be different depending on what type of overlay product you're using.
Right. And nowadays, I would almost think, or I don't have hard data to be honest, but I would say that, especially in the context of service meshes, it's increasingly popular that you essentially have mutual TLS between all the endpoints involved. So even within a cluster, even the bunch of machines where you're running your containers, even there between all of the endpoints, whatever the endpoint might be, that might be the container itself, it might be a sidecar like Envoy, for example, that even between these endpoints within the cluster, everything is mutual TLS, everything is encryption on the wire, end to end, everything is there. And then it pretty much depends on the scale, right? If you have large scale, you really want to have a service mesh that part of its control plane actually has something that takes care of the certificates, rotation, and all that beats. But in general, if you buy into that, if you are aware of the implications there, what happens, especially in a multi-tenant environment, if you're in a not so trusted environment, you're sharing resources with others, you probably want your containers, all of them, even within the cluster, being encrypted on the wire as well. And I'm not saying that all of the solutions supply that out of the box, but as I said, increasingly you do find, like Istio, for example. In Istio's case, I know there is a component in there, I think it's called Citadel, if I remember correctly, that actually takes care of that mutual TLS for every service that is there. And sometimes, as I said, you find this functionality also in what I would consider lower level, things like Cilium or Weave or Flannel or whatever, that also take care of that in the context of providing the network, and on top of that they also provide end-to-end encryption on the wire.
Right, so it really depends what you're using as to who or what is responsible for providing that safe link.
Yes.
What are some of the network plugins Docker provides, and how do we use them, or how do we go about using them?
So we talked about the plugins itself already a bit, right? In general, there are the default ones that are there, that are non-third party, whatever they're called, default or built-ins or whatever, that are essentially on the one hand Mac VLAN and also IP VLAN, and on the other hand the built-in overlay network. So this is when you say Docker Create Network, where you can directly create these multi-host networks out of the box. And everything else, the actual third-party network plugins, as I mentioned, things like Calico and Flannel and WeaveNet and Romana, Cilium and others, that, depending on what they are based on, realize things differently, but at the end of the day, more or less all address the same issue, and that is enabling applications that run in containers on different hosts to communicate transparently. So you don't need to know is the container running on the same node or on some else node. You can just from the point of view from the application, you can just use the service discovery that is the container orchestrator offers, and can just talk to that other container as if it's a local process.
Right. So what are some of the issues that often arise out of IP address management, and how are these addressed?
So in general, it's very often the reason why it's challenging is very often that you have a bunch of nodes. So you might have 30, 100, or even a couple of hundred nodes, and you have many hundreds. You might have 10, 20, 50, whatever containers per node. So you end up having hundreds or thousands of containers. And that means that, especially, and now I'm talking a little bit with the assumption that we're talking Kubernetes land, is not the case for every container orchestrator, where you essentially have this requirement, you have an IP per container. And that is something that, it means that you need to be able to carve out many IP addresses, and that, how do you go about that? How do you reuse stuff? How do you assign stuff? Do you centrally manage it? Do you somehow gossip it through the entire cluster? So the challenges there are really the combination of scale and speed, right? You need to be able to manage a large number in a rather quick way. The other challenge, which is probably not challenge, it's more to do with the fact that cloud providers still haven't widely adopted IPv6, because in IPv6 case you have many more addresses there. You don't have the big challenge there, or not as much of a challenge. But we are seeing only slowly support for IPv6 in container land. So it's not the case that every container solution has already IPv6 support out of the box. When we get there, I guess then this challenge is a little easier to address then.
Can you give us an example of how you normally go about, managing these IP addresses? Is it basically just up to the orchestrator? You just leave everything up to the orchestrator? I mean, how much manual intervention is actually involved?
So, for example, if you have Kubernetes, you're required to, and that depends a bit also on the installer and good practices around that, and environment. Are you installing it something yourself with kubeadm, for example, or are you launching a Kubernetes engine, as it's called now, cluster where you don't get to do these things directly. But at the end of the day, you need to carve out certain IP address ranges. So there are good practices there where you say, here's what you should do and here's what you should not do. Sometimes it's a matter of policy. Sometimes the organization says, okay, we only assign private ranges. It pretty much depends on the environment. Are you on premises? Are you in the cloud? What your preferences there are. But essentially, at the end of the day, you would at install time more or less define these IP address ranges. In the case of Kubernetes, as I said, you need one range for nodes, which typically is you don't change the number of nodes every day, and until you reach 100,000, you typically have a rather good idea what the number of nodes in your cluster is. Although that might through auto-scaling that might change a little bit, but it's not that you have today 10 and tomorrow 50 and the next day 500 or whatever nodes. So that is fairly doable. With pods, it's pretty tough because there can be many pods and they come and go, and every time you create a new pod, you need a new IP address, need to assign a new IP address. And services, on the one hand, they're much more stable, right? So that's the defining feature of a service in Kubernetes, that it provides a stable virtual IP, so an IP that is not connected to a network interface, so you can't ping it. But because of the implementation as it's currently done through kubeproxy, it effectively means that on the routing layer, to actually get a package to a pod that sits behind the service, it needs to update potentially a lot of different rules across all the nodes through IPTables. And that is a certain limiting factor there, which is orthogonal to the IP allocation, but still you need to take that into consideration when using IPTables directly. Yeah, so in a nutshell, pretty much depends on environment, your preferences or policies organizationally, and the container orchestrator you're using. They have different requirements for what kind of ranges you need to either before you're at install time, or if you have, typically in Kubernetes land, you would use a CNI plugin that takes care of that dynamically, which is probably one of the best ways to go about it if you can afford that, right? So Infoblocks, I know, is an IPAM driver for CNI.
Right.
But if you have a full-blown IPAM, so IP address management solution, you might end up paying someone some serious money, right? I'm not. I don't know the details about the prices, but I can imagine that it's this quality comes with probably a hefty price label there as well.
Yeah. So we're just going to move into a short section on orchestration.
Mm-hmm.
So there's a few different roles involved in orchestration, such as organizational primitives, scheduling, automated health checks, auto-scaling, upgrade strategies, and service discovery. Can you talk a little bit about these?
Right. So if you think about it, what the role of a container orchestrator, essentially it's about the lifecycle management of containers, right? So you as a user say, hey, here is my container image, run it for me somewhere. And as a container orchestrator, you have an overview of all the nodes, about how they are utilized. You might have certain preferences. You, for example, as a user could say, hey, make sure that this pod or this container, in this case, pod is Kubernetes specific, lands on a node that it has, that is SSD backed or has a GPU or whatever. Or you could say, make sure that these containers don't get scheduled on the same node. You might have, some multi-tenancy requirements, or don't schedule database containers on the same nodes as, some stateless application, whatever the policy there is. And you also have organizational primitives, which, traditionally, for example, in Marathon, you had things like groups, where you can group your applications together and then say, essentially, hard code dependencies can say, let's say the front end should only be started when the backend is available, when the backend passes all health checks. One of the innovations that Kubernetes really brought to the table, and that is also pretty well described by the Googlers from their lessons learned from, running Borg in production for more than a decade, and then trying new things with Omega, are labels. And labels are very, very lightweight and very, very flexible way of organizing things. So rather than having a hierarchical, so grouping essentially means hierarchical, fixed way of viewing how things are organized, you're labeling things. And that allows different stakeholders to manage, to group things in different ways and what is important to them. So for example, for someone, a release engineer, whatever, might say, I'm only interested in knowing, is that container in development, testing, staging, or production, right? That's all I care about. I don't care who it belongs to or whatever. I only care about that. Someone else might say, billing or whatever, internal customers might say, to me it's important, does that, is that someone who has a big budget or internal budget holder number or whatever. Someone else might say, I'm interested in how, what kind of security checks or policies have been applied. So each and everyone gets to use their labels and can query using these labels, and with that dynamically organize the view on the containers themselves as with preferences they have to do their job best. So these are the organizational primitives. And then there are a number of things that, affect or make it easier for the orchestrator to automate things like, health checking, being able to automatically scale. That's typically by default based on low-level metrics like CPU utilization, memory utilization, and increasingly we're moving over to custom metrics where you go things like, in my application, I typically have 50,000 requests per second, and now I see an increase to 80,000, and that means I want to have 3 more replicas, for example. And then upgrade strategies. So in what way are you rolling out a new version? Are you replacing existing? Do you do a rolling upgrade, and so on and so forth? And service discovery, which, yeah.
So labels are a Kubernetes only concept, are they?
Yes.
Right.
Labels to organize any kind of object. In Kubernetes, it's not, it's anything. You can, label a pod, you can label deployment, you can label a node, you can label everything. And depending on the kind of object, they serve different roles, right? An administrator might have a different use case for a label to, somehow make sure that they know what nodes there are, like, label, with different hardware characteristics, or label with in what rack they are, or whatever they need to do their job. Versus, someone in the security team looking at things like different namespaces or whatever, and labeling things there so that they know what's going on. And they are also first-class citizens in the sense of that you can query them. So you could say, give me all containers or pods, really in Kubernetes, that are owned by Kim and that are in stage production and that have not been updated for 3 weeks, right? So we have these labels, and by the selectors, by using, think a bit like SQL in a very, very, very simple way of doing, like a very stupid, naive way of doing SQL, you can combine these different labels and through the selectors get exactly the subset of, whatever kind of resource or object, pods, services, nodes, or whatever it is that you are interested in.
So what are some of the other organizational primitives?
So that's, as I said, that's originally what you would find traditionally in Marathon and other places would be things like groups, where you would have a hierarchical static ordering or organization, how you actually declare dependencies and group things and so on. And one innovation that Kubernetes brought to the table was labels and is labels. And I'm not sure if others, for example, if Nomad, Swarm or Marathon have picked it up, labels. But yeah, that's the I would argue the most flexible way to organize things. And that's nowadays I would argue the dominant, with Kubernetes being the dominant container orchestrator, the dominant way of organizational primitives there.
Right, so in terms of orchestrators, we've got the likes of Docker Swarm, Mode, Apache Mesos, HashiCorp, Nomad, and Kubernetes, I guess. So which platforms do these run on? Do they run on all platforms or?
Yeah.
Okay.
So you can think of these container orchestrators a bit like, it's a different functionality, but a bit like a PaaS, right? What do you need to run a PaaS? Well, you need an operating system, right? Typically, you need some Linux distribution or whatever, and then you can install that PaaS. It could be in a single node, could be distributed, whatever, but pretty much the same thing is happening there. And originally, as I said, it was called container orchestrators. Typically nowadays, the marketing term is CaaS, so container as a service, right? Like PaaS, platform as a service, this is CaaS, CaaS sometimes. So, if you want to be cool, you go like, hey, which CaaS you got? And then you got, Kubernetes, Docker Swarm, Mesos, Nomad. Now, it was quite interesting for some, let's say, 3 years, from roughly 2014 to 2017. And remember, before I joined Red Hat in beginning of 2017, I used to work at Mesosphere on Mesos, Marathon, DCOS. So around that time, from 2015 to 2017. And that was pretty much the high point of the container orchestration wars. So that was where no one really knew, because Kubernetes was very new, just came out. Docker Swarm was, Docker, everything was Docker, so it sounded like, and the idea was that, maybe Docker would make it. And Mesos Marathon had also quite a big mindshare. So it was at some point in time, you could say, you would have 2 or 3 equally powerful and widely used systems. Then later on, HashiCorp entered the container orchestration with Nomad, which has a slightly different focus and orientation. But essentially, we besides those, we obviously have many more things that also started to do containers. All the configuration management systems somehow started to do container orchestration as well. And at the end of the day, by 2017, end of 2017, Kubernetes essentially won this container orchestration war. So you can nowadays, it doesn't matter who you ask. It's a bit like, yes, there are people that use FreeBSD and NetBSD or whatever, but Linux is dominating pretty much everything. 90% or whatever is Linux out there. And in the same way, like it or not, Kubernetes has with beginning of 2018 has essentially, it's supported everywhere. Everyone has to, even big Amazon at some point in time, AWS had to also support Kubernetes in their offerings. So it's fair to say that nowadays Kubernetes is the dominating container orchestrator. That doesn't mean that the others are gone. People still are using Swarm, still are using Mesos and Marathon and Nomad. It's just that nowadays there is no question if you want to get into that game. The question is just, should I directly jump to function as a service, serverless, Lambda, Or should I still be dealing with containers? But the question is not, should I be doing Meso, Swarm, or Nomad or Kubernetes? If you wanna have a good guarantee that your knowledge is directly applicable, then maybe Kubernetes is the best choice now.
Yeah. So you mentioned nodes a few times. Are they a Kubernetes concept? I'm assuming they're a host for a container or a collection of containers?
Yes.
Yeah, right.
It's just a host. Like the technical, the Kubernetes documentation uses node or worker node as that's the one host or the one virtual machine or physical machine that actually hosts the container runtime and the other bits that are there, kubeproxy, the kubelet, and so on, that runs the containers for you. Yeah.
So what are the main components in Kubernetes, and what are they responsible for?
Right. So in a very high level, there are two parts in Kubernetes. The one thing is called the control plane, previously called the master. I find control plane much better because it's actually is it's not just one binary. It's a couple of things. It's the API server, the controller manager that implements all the control loops. If you, for example, are dealing with deployments and services and whatnot, for each of these resources, you have a respective controller, which technically is just a Go routine in the controller manager. And then you've got the scheduler that actually does this mapping of here you have a container or actually a pod in Kubernetes, and here is a node where I'm running this pod on. So the decision on which node to launch a pod. And then you have the worker nodes. Typically, nowadays you might have 20, 30, 40 nodes usually. And on each of the worker nodes you have at least 3 things running. The kubelet, which you can think of the kind of like the local supervisor. So right, in the same way that you have the API server that uses etcd to keep its state around. In a control plane, you have, as a local node level supervisor, you have the kubelet that then talks to the container runtime, which is, for example, Docker, OCI-based things like runc or whatever, Rocket. So the container runtime that actually knows how to pull a container image from a registry, how to launch that container, and so on and so forth. It manages the lifecycle of a single container. And then you have kubeproxy, which is part of the Kubernetes service discovery story and realizes and establishes these virtual IPs for the services. So essentially make sure that there is traffic that comes from within the cluster from some other pod and finds its way to a certain pod that sits behind the service. So these are the components that run on each of the worker nodes. And obviously you need a container registry for the runtime to pull the container image. And then, at least in case of Kubernetes, you need typically what an admin takes care of, some kind of external user management. So Kubernetes doesn't, you can't create users or whatever. There are identities for applications called software service accounts, which represent identities for applications, but Kubernetes doesn't, it can understand, this is the user and this is the group or whatever, but it doesn't manage users for you. So you need some LDAP, Active Directory, SAML, Kerberos, whatever, something external that manages your users and group. And then you can, you have integrations to bring that into Kubernetes.
Can you give us a bit of an overview of Kubernetes networking? So containers can communicate with all other containers without NAT. Nodes can communicate with all containers and vice versa without NAT. And the IP container sees itself as the same IP as others see it. Is that correct?
Right. So what's interesting there is, I think, the fact that Kubernetes is not prescriptive there, right? Kubernetes essentially just says, look, here are a couple of requirements I have, and how you realize them, I don't care, as long as these 3 requirements that you mentioned are met, right? So there is no netting. There is technically it's per pod. So a pod is a collection of a couple of containers that are guaranteed to be scheduled on the same node. That each of them can communicate with any other in that container without any netting, right? So each pod has its own IP, gets a new assigned if it restarts even on the same node, has always an IP. And the nodes can talk to the containers and the containers can talk to the nodes and amongst each others without netting. And also, which is also different to Docker, where depending on what you're using, you have different IPs that you see from the outside world and the inside world. That, the IP the container sees itself is the same that others, other hosts or containers or pods in the network see that container. And that is essentially because it's not prescriptive. It just says here the requirements, leaves a lot of flexibility to how you implement it, right? You can do that bare metal with some manual configuration. You can use any kind of SDN there. The downside is, however, that because Kubernetes doesn't supply anything out of the box there, that you effectively are forced to roll your own Kubernetes distribution, right? This is one of the decisions that you, if you want to use Kubernetes, you need to make, right? You cannot, there is not anything out of the box like you have with, in Docker's case, with the Docker overlay network that you can just use, right? So at the end of the day, your decision is either I roll my own Kubernetes distribution, and there are other bits and pieces where you also need to make decisions where you say, okay, especially on premises, what kind of storage am I going to use, or ingress, how do I get traffic in there? So there are a couple of other things, but most importantly, this Kubernetes networking, there's nothing out of the box there. So if you don't do it yourself, then you can use one of the over 30 certified Kubernetes distributions. But at the end of the day, you need to use a Kubernetes distribution, right? In the same way that you cannot use the Linux kernel on its own, you need to have a Linux distribution. In the same way here, you have you're dealing with a Kubernetes distribution, and if you roll it on your own or pay us or someone else to do it, that's a different discussion, right? That's buy versus build. But you have to deal with a Kubernetes distribution, and one of the main reasons is exactly the Kubernetes networking.
Okay. What are some of the distributions?
There are so many. As I said, there are over 35 or whatever. One of them I can talk about. That's what pays my bills. Is OpenShift. Has been around for quite a while, but there's so many. Like typically, the most interesting one I would argue is if you are using one of the managed Kubernetes services of the big three, right? So if you're in Google or Azure or AWS, then each of them obviously has their own Kubernetes distribution. They typically are not very public about that, right? It's just there. You don't really get to see the bits. And I mean, of course, you see, sometimes you have options. You can say, okay, I want to use Flannel versus Calico or whatever. And there are certain preferences as well of the cloud provider towards certain solutions, but you don't really get to see how the whole distribution looks like, right? And then there are, very minimal ones that, try to be very opinionated, but very lightweight. There are things like OpenShift that, on the one hand is a Kubernetes distribution, but on the other hand also provides a lot of PaaS functionality, ships with a container registry and the build system and so on and so forth. So, as I said, there are currently already over 30 certified. So the CNCF, the Cloud Native Compute Foundation, essentially has a very lightweight process. And she says, okay, here are the conformance tests, run them. Yeah. So each and everyone can just simply, figure out for themselves if they are compliant or not. And once you're done, you send it in, and then since it's so transparent, there is no politics or whatever involved. If you pass it, you're conformant, and you can call yourself a certified Kubernetes distribution.
So say I'm a developer and I want to set up some orchestration on Kubernetes locally so that I can test it. Can I just set up a Kubernetes distribution locally in order to develop and test? Is that easy enough to do? Yeah.
So typically, for developer workflows, you would have things like Minikube or Kubernetes as part of Docker for desktop.
Right.
There's Minishift, which is OpenShift out of the box in a VM. So essentially what you have is more or less, in all cases, you have a VM that essentially wraps up all the dependencies, has essentially a single node setup. And all you need to do is, depending on the kind of offering, sometimes it's CLI only, sometimes it's a nice clickety-click UI, but you essentially just launch a VM that has all the components in there. And they're actually pretty great. They're for most things, they're perfectly okay. Obviously, what you can't really do is having the effects of a real distributed system I'm not even talking about scale testing or whatever there. I'm really talking about, what happens if you have network partitions and delays between different nodes and so on. You simply cannot do that which is obvious, right? If you have everything in one VM,
Right.
you simply cannot know how your application really works in a distributed setup. But for, I want to try that out, I want to quickly deploy something, whatever, they are perfectly fine and very straightforward to set up. There is not much that you need there. I mean, you need some VM driver there, get it from VirtualBox or whatever, but very straightforward to set up.
Okay, so I've got another section on service discovery. We're getting sort of pretty close to time. I'll just see if I can spring a couple of questions. In terms of registering a container, what happens when the scheduler dies and the registered containers keep running? Essentially, the containers are now running rogue. Is that correct?
Yes. So essentially, it's pretty much the case with all the different container orchestrators that if the scheduler or whatever it is, might be the API server in Kubernetes case or whatever, a control plane component dies, then all the containers on the worker nodes continue to work. They don't notice that. The only thing that you cannot do is you cannot do updates. You cannot, for example, roll out a new version, or if one of the pods or containers dies and it will not be scheduled somewhere else because there is no control plane around to figure out that this container has died and needs to be launched somewhere else. So as long as you don't have any network service discovery related, depending on some FQDN or whatever that is not there anymore, or that doesn't resolve to an IP, you should be fine, right? So everything, and typically, you typically, if a scheduler or API server or whatever dies, you're typically trying to get it back up and running in a certain point of time. Right? So you're not, letting it in that state for weeks and weeks, but you're trying to fix that. And if it comes up within an hour or two, that's fine, right? And typically also dealing with a couple of replicas there. So if you only have one replica of a pod or of a container there, then maybe you're in trouble. But if you have a couple of them and then due to whatever reason one of them or two of them dies, okay, maybe your application slows down a bit, but it's still there and it's still serving.
So when the scheduler comes up again, does it find the rogue containers? I mean, how does it go about finding them?
So this very much depends on the container orchestration system, but at the end of the day, what happens is you have on each of the nodes, you have a local supervisor. So in case of Kubernetes, that would be the kubelet, and that essentially sends heartbeats to the control plane component saying, I'm still around, I'm still good, and maybe in cases usually also saying like, hey, I have so many containers running, and I have this memory pressure or whatever other status information it sends to the control plane, and so that will just continue, and as long as things are happening on all of the different sides, so both in control plane and on the node or nodes, it just restarts and self heals, and at some point in time picks up where it has left off. If the state, if the distributed state or the cluster state is not corrupted. That is probably the hardest bit, right? If for example, in case of Kubernetes, if etcd is down, you can still, it's the same. It doesn't really matter. If etcd is down, then you can change the state, right? It doesn't really matter if the API server is up because you can't change anything. You cannot read, you cannot write the state. It doesn't matter. So the assumption really is, that's why you typically run 3 or 5 etcd servers there together, that you have a guarantee, pretty much a guarantee that etcd never goes down. And what's etcd for Kubernetes? It's Zookeeper for Mesos and so on and so forth. So each of the container orchestrators has their typically distributed key value system that has this is the ultimate system of records that knows exactly the state of the entire cluster.
Yeah, so does that component go down occasionally as well? And if it does, I guess basically you've just got to shuttle your containers down.
Right. Yeah.
Yeah, right. So I've also noticed you've got the Kubernetes Cookbook, right, and you've got the Kubernetes Security book that you're working on. Are they done, or are you still working on those?
Yeah, so the Kubernetes Cookbook came out in March, I believe. So that is out there. It's as far as I gather, quite successful. So a lot of people, I get, people telling me it's cool, and I see it online and whatnot. Kubernetes Security, which I'm writing with Liz Rice from Acqua Security, we literally just submitted the final draft. So we're now going in production. And I think it should be out by end of 2018. So October, November, who knows, around that time.
Cool. Looking forward to those. especially the security one.
Cool.
So, yeah, thanks for joining us today, Michael. It's been educational and fun.
Cool. Thanks a lot for having me, Kim. It was really fun.
For Software Engineering Radio, this was Kim Carter, your host. Thanks.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio. Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.